So we're going to continue with question 6.5. A simple Rankine cycle requires 2 megawatts of heat in the boiler and rejects 1 megawatt into a nearby river. Assuming the work of the pump is negligible, determine the thermal efficiency of the cycle and the power produced by the turbine. Right? So this is similar to what we just did before, but instead of a refrigeration system, it's a heat engine. Specifically, this is a Rankine cycle, and we're told that we can neglect the amount of work in the pump. And this is very common when we work with Rankine cycles, because the work that the pump needs to do to compress a liquid is much, much smaller than the work that a compressor in a Brayton cycle needs to do to compress air. So let's just draw it out. We have our hot area here. We have our cold area. So the hot area is the boiler, and we're putting into the heat engine, we're told 2 megawatts, and we're rejecting into the lake via a condenser 1 megawatt. And of course, the goal of any heat engine is to produce the work output. And it's pretty simple. We look at the energy balance and what's going in and what's going out. Work output, by the way, is produced by the turbine. So what's going into the system? Well, we have 2 megawatts going in and the rest is coming out. We have work out leaving the system and we have the Q out leaving the system. And clearly we can see right away that the work output is equal to 1 megawatt. So what does this mean? This means that we have some steam power plant cycle. We're giving it 2 megawatts. We're getting 1 whole megawatt that we get to use as useful work, whether that's to spin a generator or to do anything else. This is the amount of work that we actually get to use. Of course, we also see that we're wasting 1 megawatt of that work as our Q out. That's what's being rejected into the river. And this leads us to the second part of the question, which is asking us about the thermal efficiency. Now, the thermal efficiency, again, whenever we talk about efficiency, what we're talking about in general is how much we get versus how much we have to give. So what do we get? What's our goal of the system is to get a work output, right? Work out is what we get. And what do we have to give? What's the price we have to pay? Well, it's our Q in. So whenever we want to have a big thermal efficiency, we want a huge output of work for as small of a Q in as possible. So in this case, we know our work output we just calculated was 1. Our work input was 2. Okay, so our thermal efficiency is clearly 0.5. That means 50% of what we put in gets converted into work. Now, that might not sound like a lot, but in general, when you work with the Brayton and Rankine cycles, you'd expect to see something between 30 and like at the highest 60 in that range. So 0.5 is actually not as bad as it sounds.